Our lives are the biggest soap opera with way more complicated plots. A drama of this magnitude requires a screen of universal proportions. Physicists call this space-time. Let's think of space as a tightly held bed sheet. Placing a heavy ball on the sheet causes a depression. A lighter object close enough will be pulled inwards. Similarly, a massive planet distorts space around it. Greater the mass, greater the distortion. The depressions caused are gravitational fields. In empty, undistorted space, the planet would move along a straight path, following the lines of space, and would not deviate unless acted upon by an external force. When space is distorted by a massive object, the planet still moves along the lines of space, but now these lines of space are curved. Hence, the planet describes an elliptical orbit. This is just like swinging a ball on a string overhead. If you release it suddenly, the ball continues off in a straight path. Now, let's look at gravitational waves. These waves involve the stretching of space itself. Imagine space as a sheet of graph paper. A gravitational wave will stretch space along one axis and compress it along the other, and this alternates. The actual stretching of space is so small it would have gone undetected had we not built LIGO, which by the way has nothing to do with plastic blocks. About 1.3 billion years ago, two black holes supposedly merged to form a single, more massive black hole. Tremendous energy was released, and gravitational waves powerful enough to reach us were detected in 2015. But why did it take us so long? Well, because gravitational waves travel at 300,000 kilometers per second, aka the speed of light. Making things simple, LIGO consists of two long evacuated tubes. A beam of light from the same source is split and sent along these tubes and is reflected back by mirrors. The split beams meet at the intersection of the tubes, and the pattern formed by their interference is visible. This whole setup has to be done as precisely as possible, or else the pattern can't be seen. If a gravitational wave passes through the setup, it increases the length of one tube by a tiny amount, and therefore increases the amount of time it takes that beam of light to meet with its twin, and this affects the pattern formed by a small amount. Scientists studied these differences and thus concluded that gravitational waves were detected, but only after verifying these results with LIGOs at other places on the planet too. So why are gravitational waves so important? Well, they are ripples in space itself. They can pass through matter without being affected, unlike light. Therefore, they are key to understanding our universe. The frequency of gravitational wave detection is steadily rising, but if you're like me, even the sheer awesomeness of gravitational waves should get you excited.